All righty, so welcome today to our third in our DAT OAT prep series. We're talking a little bit about organic chemistry today. So that is our plan, and I'm trying to get one more person in from this room, but they won't come in. Something's keeping them from getting in. Sorry about that. All right, so today we're dealing with organic chemistry and how it all works on the DAT and the OAT. So just a reminder, the organic chemistry comes at the end of the Survey of Natural Sciences. So I've said this a couple times. I'm going to reiterate this again by saying that the timing is everything here, because organic chemistry, you're going to need the most time to do these questions. So you don't want to like be wasting that too much time in the bio and the GChem questions. So you got to get onto these. It's the same place on both the tests. And so here's the biggest issue I think comes with the organic chemistry on the DAT. This requires you to know all of your reagents. So if you still have those flashcards or whatever else you had there during your organic class, I would suggest you dust them off and get your reagents rememorized and your mechanisms rememorized, because it is necessary. Both of those things are necessary for the DAT and the OAT. Understanding the individual steps, what arrow pushing is, like how to, string synthetic steps in a row. All of these things are very relevant to the MCAT, or sorry, not the MCAT. I was just looking at something that said MCAT, to the DAT, the OAT. All right, and spectroscopy as well is on this test, but you don't have to remember lots and lots and lots of frequencies for the DAT, the OAT. Knowing just your basics, about where stuff is going to show up, what splitting means, and NMR in infrared spectra, like knowing where carbonyl, OH, and CH are, that's basically the big ones. That's going to be good enough. You also need to make sure you remember how to assign chiral centers and E versus M and cis versus trans and things like that, as well as nomenclature rules. And then finally, you have to be able to deal with aromaticity. Like, what is aromaticity? What is resonance? Resonance, recognizing aromaticity when it's present in a structure, recognizing resonance structures and their contribution to the overall resonance structure as well. So all of these things are very relevant to the DAT OAT. So basically, all three of the classes that you took in organic are going to be there. So A, B, and C. Don't you wish you were taking the MCAT now? Because the MCAT actually doesn't have nearly as much organic chemistry on it. So let's look at a few of the questions that you might run into on your DAT OAT. So here's just right from the beginning, 72. The first question of organic is 71. Which of the following alkyl bromides will most readily undergo SN2 reaction with NaOH? So does anybody remember what it is they're getting at by asking about this in terms of SN2 and looking at the molecules themselves? What is the nature of the SN2 mechanism they're actually asking you about in this question?
Isn't it backside attack?
Yes, exactly. This is about the steric hindrance on the backside of that nucleophile or the electrophile. So AA, what were you saying?
Sorry, it's been a long time since I took organic chemistry, so I don't really remember. But all I remember it was the mechanism, which is backside attack. But I'm not sure which one. What would the answer?
Looking into like primary carbon. Or
so do we want something that's more sterically hindered or less sterically hindered if we need to attack from the backside?
Less
Sterically hindered. So which one of these alkyl bromides is the least sterically hindered? Here we've got a tertiary, we've got a secondary, we've got a secondary, we've got a primary, and we got an aryl. And these just straight up don't react. So what's our least sterically hindered?
D.
D is our answer. Yep. So that's what we're supposed to remember, is things like that about our mechanisms. It's like, okay, something as simple as remembering backside attack is enough to answer this question, but you got to remember what that means. That it's, we're looking at the steric hindrance, which means we're looking at primary versus secondary versus tertiary, and so that you can recognize that in the question. I mean, you could do some eliminations on this, knowing that benzene rings don't do this, and both of these are secondary, so they're going to be the same. And so we're narrowed down to our extremes of primary versus tertiary. So if I had to guess, at least I'm 50-50. But fundamentally, knowing what your mechanism is searching for is what we need to use here. All right. What about this one? Which of the following intermediates is most likely to be involved in the reaction shown? So again, thinking through the mechanism. What kind of an intermediate occurs in an electrophilic addition reaction that you would see here? So this is our electrophilic addition reaction. What intermediate do these things produce? Anybody remember? We've got two choices. It's either a cation or an anion. Well, what do you guys remember about carbanions? Stable or very unstable? OChem has been promptly forgotten, hasn't it? Very unstable. Yes, thank you. So carbanions are very unstable. So what do you think about those as intermediates? Good or bad choice?
Bad choice.
Very bad choice. Let's get rid of those. We're not going to form carbanions because they're just DAT unstable. And we're also not going to form radicals because that's not the kind of mechanism this is. This is going to be cations. And then the first step of this reaction is going to involve an electrophile. So is the chlorine an electrophile or is the hydrogen an electrophile?
Hydrogen.
Because it's partially positive. We got this partially positive hydrogen. We got this partially negative chlorine. The hydrogen is my electrophile. So what's our correct answer? Where H attaches to it, the electrophile in A, or where Cl attaches to it? Yeah, A, where the hydrogen attaches, not the chlorine. The chlorine comes in the second step of electrophilic addition. So again, what it sounds like is we've forgotten our mechanisms. Does that sound appropriate? Does that sound like people are in agreement with that? We don't remember the specifics of our mechanisms right now? Yep, and that's what you're gonna need to recoup, like get that stuff back in there. These are things you did once know when you took organic chemistry, and so it's just now gonna take going back and reviewing it to get that back in there. All right, here's a spectroscopy example. Strong infrared absorption between 1750 and 1700, 5.71 to 5.88 microns. That's just a different way to measure those frequencies. But I bet you guys can remember this one. What very large frequency or large signal occurs between 17 and 1750?
Carbonyl.
Carbonyl. That's our carbonyl. So this one should be a freebie question if you remember your spectra. It's almost always going to be carbonyl or OH or NH2 that you're going to see on these things. OH and NH2, they show up more like OHs show up around 3400. NH2s show around 3500. These are short and broad. Or sorry, tall and broad. These guys are short and broad. Like just being able to recognize the types of peaks when you see them is important. You probably won't be interpreting spectra on the DAT or the OAT, but you might get asked like specific frequencies like this. So you just got to brush off a little bit with your spectra and try to remember what some of those frequencies are. Again, this is a lot of memorization that you're going to have to do here. This is where Anki can be very helpful, is studying for organic chemistry. So here's another one. I know this one's a little bit small. Which of the structures below is an important resonance form of the anion shown below? So we're looking for an important resonance form. So should my resonance form have a different charge or the same charge? Considering that resonance is just moving electrons around, it should have the same charge. So same charge for the same resonance or for a different resonance structure, because all resonances is moving electrons around from place to place. So do any of these have like fail in that department? A actually doesn't fail from not having the same charge because it does have an overall negative charge, because it's -1 + 1 - 1 adds up to -1. It fails for a whole nother reason, is that do we like separation of charge? Is separation of charge a good thing?
No.
Nah, we don't want to separate our charges into 3 charges. So A fails for that reason. D and E fail for having the wrong charge because those are both neutral somehow. Somehow the
B.
charge just disappeared in there. Okay, and then if I'm looking at B and C, those both have a single negative charge. What's got to be my correct answer?
B.
B has to be the correct answer because we can't move atoms around. If this carbon has 2 hydrogens on it, then that carbon must still have 2 hydrogens on it, but C shows only 1 carbon on it or 1 hydrogen on it. That's got to be out. So resonance is only moving what? Atoms or electrons?
Electron.
Resonance is only moving electrons. That's right. So we're only moving electrons around, not atoms. Electrons, not atoms. And we got to remember again, resonance, separation of charge. We got to know that concept. The minimization of charge, we got to know that concept. And why is it a fairly good stable structure in the case of B? Where's my negative charge? On a more or less electronegative atom?
More electronegative.
So negatives tend to be on more electronegative, positives tend to be on less electronegative. So our basic rules for resonance. And then the isomer questions begin. They usually come in the 80s. And these are all rough numbers, but usually you're going to start seeing your nomenclature and your RS, EZ, isomer type questions when you get to the 80s. So, all right, I'm looking at this one, and there's actually some answers I can get rid of pretty easily here. First off, should I ever pick meso compounds with an S? Is meso plural or singular?
It's a singular one. Meso having a plane of symmetry with itself, I believe.
So meso is a singular. You can't have meso compounds. So putting the S on it negates it as a correct answer. It can't be right. Don't pick a plural meso compounds. Are these things identical?
No.
I mean, one's got a wedge and one's got a dash methyl. The other one's got 2 wedged methyls. These are not identical. Are they structural?
Yes, the same structure.
But does that make them structural isomers?
No.
Because structural isomers should have distinctly different connectivity. These have the exact same connectivity. All the same atoms are connected to the same atoms, which means we're down to enantiomers versus diastereomers. And I know that you guys were taught non-superimposable, non-mirror images or enantiomers and diastereomers, and superimposable mirror images are non-superimposable mirror images are enantiomers. That's a terrible definition. Let me teach you one that's really straightforward definition. For enantiomers, what I want you to remember is you have to have 1 or more chiral centers and they're got to be all opposite. So these compounds have how many chiral centers in them?
Two.
Agree or disagree? Yep, we got an agreement. Yeah, each one of them has 2. So it fits the enantiomer definition, but are they all opposite? Is this first one on the left opposite? Methyl on the wedge, methyl on the wedge. Are those opposites of each other? Are they the same as each other?
Same as each other.
So those 2 are identical. So does it fit with my enantiomer definition?
No.
These are not enantiomers because they would all have to be opposites. These are not all opposites, which means they must be diastereomers. A nice test prep diastereomer definition is it has to have 2 or more chiral centers with only some of them opposite. And this fits that definition because I've got 2 chiral centers and only one of the 2 is opposite. The second one is wedge methyl versus dash methyl, which is opposite. In fact, that's also the definition of epimers. If I'm epimers, I am a set of diastereomers, which means I have 2 or more chiral centers. But how many are opposite if I'm an epimer? Just 1. So enantiomers, 1 or more chiral centers, all opposite. Diastereomers, 2 or more chiral centers, some opposite. Epimers, 2 or more chiral centers, only 1 is opposite. Because in the first case, on the left, the methyl is on a wedge and the methyl is on a wedge. That is the same orientation. All the atoms are attached to the same types of parts. Wedge for the hydrogen, or dash for the hydrogen, wedge for the methyl, sticks for the other 2 groups. Here, the wedge is a hydrogen. Here, the wedge is a methyl. And it got flip-flopped with the dash methyl and the dash hydrogen. So those 2 are opposites because the methyl and the hydrogen have swapped places. Do you see that? All right. So that's what we're looking for with opposites here. So enantiomers, diastereomers, and epimers, it's easier to look for them in this capacity because this is something you can point at and count instead of thinking that whole non-superposal mirror image crap. Like, forget that stuff. That's horrible. And then meso, how many chiral centers does something meso have to have? Can it have 1? Can it have 3? Can it have 5? Or does it have
2.
to have 2, 4, or 6?
2.
Or 4 or 6. It just has to be even. It has to have an even number of chiral centers, and it has to have internal symmetry. That's why it has to have an even number of chiral centers, because if you have internal symmetry, you can't have an odd number of chiral centers, because the plane of symmetry would have to go through that odd one out, which means it's not actually symmetrical. Or an internal plane of symmetry, which is what I think I'm getting out from the chat there. Just in time for Halloween. All right. So sometimes what it takes is redefining your definitions in a more test-friendly way. And you know, it's going to help more on a standardized test to think about the isomers this way than to think about them in terms of their non-superimposability. Then there's just straight up Iupac naming. Let's see, what do you guys think this one is? They all end in -ene, so that isn't helpful. What's my longest carbon chain? Looks like hex, I would agree. So let's get rid of our pent, and our propylene. And then it's either 3-methyl-5-hexene or 4-methyl-1-hexene.
I think it's 3-methyl-5-hexene.
So you're numbering from left to right.
Yes.
Don't do that. That's probably the trap, because the higher priority group is the functional group, the hexene, which means that's forced to be carbon 1. The answer is A. And this is actually something I've noticed on a lot of standardized tests with nomenclature problems, is that they tend, and your teacher probably did this to you too, they tend to orient it so the numbering is not going to go left to right, it's going to go from right to left. Because out of habit, what do people generally do? Read from
Left to right.
left to right. So we usually just out of habit, we just normally will go left to right the way we do things. And they're almost always going to intentionally flip it around so that that left to right orientation will be wrong. It's not always, but it's pretty close. I think I've seen, you know, several dozen of these in the last couple of years on different various tests. And it's pretty common for them to orient the numbering from right to left. So be cognizant, God, that's a hard word, cognizant of that, and like look for the right to leftness of it. If it's not there, then go left to right. Okay. And here's a straight up reagent question. I call these reagent questions because they're really looking for one of several of your different reagents, being oxidizing agents, reducing agents, acids, and bases. Acids and bases, oxidizing, reducing. So what's happening to this molecule in this reaction? Is it being protonated, deprotonated, reduced, or oxidized?
Oxidized.
And how do we know that it's being oxidized? Because that carbon is gaining.
Well, there is an addition of oxygen.
So that carbon is gaining an oxygen. That's how we know that it's oxidation. Now, like, and I'm narrowing it down to these 4 things because that's generally what we're going to be seeing. And in this group of reagents, there is only one oxidizing agent. And do you guys remember the shortcut I gave you for recognizing oxidizing agents last week?
No.
Reducing agents, mexes and moxes. Mexes and moxes. MEHX are reducing agents. So what is A? Is A an oxidizing agent or a reducing agent? It's a reducing agent because it's MEH4, which is MEHX. It's a MEX. So that's reducing, which means it's not a good answer. What is B?
How did you define MEH? What do you mean by?
So B is an oxidizing agent because it's an MOX. It's a metal with oxygens. So that's our best answer. And MEHX, metal, M, element, E, hydrogens, 4 of them.
Oh, okay.
It's just a placeholder chemical formula. Mexes are reducing agents and moxes are oxidizing agents. Socyl and Pieber and Pekel, these kinds of compounds, these are halogenating agents. They're like the sort of 5th cousin to these types of reactions, these types of questions. They both do the same thing. Neither of them can be correct. They're both halogenating agents. What is E?
It's acid.
Acid. That would protonate. That's not what we're looking for. And I don't have an example of this, but if I did, I might have OH minus, which is what?
A base.
A base. And that's going to deprotonate things. So this actually, the setup is very common in the answer choices. You'll see this 2 or 3 times on any given test. And you want to be aware of it, watch for it, where you're given combinations of reducing agents, oxidizing agents, acids, bases, and halogenating agents. And it's just a one step, you catch what's going on in the reaction and pick the correct reagent for it. So I usually just call in my head, this is just a reagent question, because you'll just have to figure out what type of reagent it is, not specific reagent, but what type. And usually what they do is they'll actually have one of each, a reducing agent, oxidizing agent, halogenating agent, acid, and base. This one's a little unusual. All right. You also have to deal with acidity and basicity of organic compounds. So this is your classic acid trap question. What is the most acidic proton in this compound? I'm going to tell you, it's a trap.
It's A.
Agree or disagree? I would agree, because why else do we call that functional group what we call it? What is the name of that functional group?
Carboxylic acid.
It is a carboxylic acid, because that is the strongest acid in there. Now, what will happen is right now it's probably easier for y'all to see this is A. But the trap comes when you learn about alpha hydrogens. And if you've just studied about alpha hydrogens, I will guarantee you're not looking at that proton. You're looking at B as being one of the most acidic. And B is still not even the second most acidic. C is the second most acidic because it's an alcohol. So if I had to rank them, I'd go A is more acidic than C, or sorry, E, I guess that is more acidic than B, is more acidic than either C or D. But alpha hydrogens are acidic. Carboxylic acid hydrogens are acidic. And alcohol hydrogens are acidic. Again, another pretty common question to ask about acidity of protons in a hydrocarbon or a hydrocarbon-based structure. And which of the following is aromatic? Oh yeah. So 2 of these straight up can't be aromatic, because aromatic must be a planar ring. Which 2 of these are not planar rings? B definitely not, because it's not a ring. It has to be a planar ring.
E.
E is a planar ring. Planar, flat. It has to be flat. Which one of these is also not flat? There you go. There's a pucker to D, right? We can see it visually that it has a pucker there. It does not lie flat. Now, the rest of these are somewhat traps. C looks pretty good. Not planar. You have to recognize cyclooctatetraene as a non-planar structure. It actually adopts this weird structure like a boat, because if it were planar, it wouldn't be aromatic. It would be the opposite of aromatic. Does anybody remember what the opposite of aromatic is? Organic chemists are not clever in their naming, so it's not aromatic, so we would call it, what prefix means not in organic?
Aromatic.
Anti-aromatic. Not non-aromatic, because non-aromatic is what B would be. B is not aromatic. Anti-aromatic is the opposite of aromatic, which means it's unstable. So if you have to rank them, you've got something that's not aromatic, it's just normal. You've got something aromatic, which means it's nice and stable. and you've got something that's anti-aromatic, which is nice and unstable. It actually destabilizes the structure to be anti-aromatic. So C will go non-planar simply to avoid being anti-aromatic. And it is the potentially anti-aromatic case because it has 8 pi electrons. So the anti-Huckel number of electrons. If you remember, aromatic has 2, 6, 10 is its Huckel number of electrons. Anti-aromatic is all the other ones, 4, 8, 12, etc. So what is A, aromatic or anti-aromatic?
Anti-aromatic.
Because A has 2 double bonds, that's going to be 4 pi electrons. That's going to be anti-aromatic. And there's nothing something square can do about being anti-aromatic. It must be anti-aromatic, which means E must be our aromatic case. But how many electrons does E have in its Huckel number? Oops, I didn't mean to cross that out. So E has how many Huckel electrons?
6.
But wait, isn't there a lone pair there? Doesn't that count? No, it does not. It is 6 because only the pi bonds count. Pi bond 1, pi bond 2, pi bond 3. That lone pair does not contribute to the Huckel number. And I was surprised when I saw that this particular practice question didn't have the lone pair drawn in. I would suspect that they're going to have the lone pair drawn in on it. Because why? What does that make people do?
Confuse.
Yeah, it makes people count it and it'll get you confused. So my bet is on the heteroatoms, you will see the lone pairs drawn in, and you have to remember not to count them because they do not contribute to the pi system. Oh no, synthesis, really? So towards the end of the section, you're gonna get, like, this is question 100, but you're gonna get like 3 or 4 of these guys. This is a 2-step synthesis question. Sometimes you'll get 3-step synthesis questions. And so what you got to do is you've got to figure out what do each of the reagents do as you go. So what is number 1 again?
Reducing agent.
And we know that because what's that abbreviation we could use to remember our reducing agents?
Max.
MEX is MEHX. So I've got a reducing agent here and a carboxylic acid. So if I reduce a carboxylic acid, what am I going to reduce it into? Carboxylate wouldn't be reducing it. That would be just deprotonating it. If I ended up with carboxylate, that would be this guy, COO minus. So if I want to reduce it, I got to take away what? Take away oxygens. So if I'm going to take away oxygens, I'm going to just take one of those away, and I'm going to be left with an, what's a carbon with a single oxygen on it? It's an alcohol. So I'm going to convert that carboxylic acid into an alcohol. And you've got to remember this one because like other reducing agents are like won't get it all the way to an alcohol. Lithium aluminum hydride is a very aggressive reducing agent. So it's not going to leave it as a ketone or an aldehyde. It's going to leave it as a alcohol. If I were to use, say, D-bol, diisobutyl aluminum hydride, then I'm going to get carboxyl, or sorry, an aldehyde in this case. I would stop at the aldehyde stage because I'm using a deactivated form of lithium aluminum hydride. And I'm betting a lot of people do not remember DBAL, D-I-B-A-L-H, A-L-H, DBAL. It's the reducing agent that's very similar. It's just a deactivated form. So now I've got this alcohol and I'm going to add HBr to it. What mechanism am I looking at now instead of reduction? I'm going to be looking at halogenation, but more specifically, this is going to be an SN2 reaction because I've got a nucleophile, the bromide, and I've got, actually it's probably SN1 because I've got the H+. So it's an SN1 substitution reaction. So what's my final product going to be since it's substitution? Not A, because my carbonyl's gone, right? The carbonyl was taken away in the first step. So those won't be right. B, nope, that's too much substitution. Count your carbons. Generally speaking, the number of carbons is not going to change. How many carbons are in B? How many carbons are in B? There's 6. How many carbons did I start with in this thing? The OG has 7, that's right. The original. So the original has 7. So generally speaking, you should keep your carbon number the same, unless you're using something like a Grignard or something that actually adds carbons to the structure. So we either got 7 to 6, that means B is out. What's our correct answer then? Yep, answer choice C. Because D has the right number of carbons, but we don't get the halogen. So boom. So got to remember those reagents, but there are a few little rules to remember. I think the carbon rule is generally the most important one to remember, is that don't forget that the number of carbons is usually going to stay static in most chemical reactions. You generally can't break carbon-carbon bonds or make carbon-carbon bonds. So it's almost always going to be just keeping the same basic carbon framework and moving stuff around that's attached to it. Maybe changing the position of a double bond or something like that. Phew. So how you feeling about OChem right now? Better than GChem? Fair enough. Most people forget over OChem because like it's like use it or lose it kind of thing. So it's really what I think it takes is with OChem, one of the things you've got to do is just you're gonna have to relearn, not relearn. I don't want to say learn because you're not learning things again, but like remembering what's the important stuff, right? You've got to get back in your mind what all these little little details are. So like if you're currently in OChem, this helps you a little bit know what to focus on, to be honest. It's not just the memorization of the mechanisms, but like things like this, understanding what different reagents do, that these reagents reduce, these reagents oxidize, these reagents protonate, these reagents deprotonate, these reagents halogenate. These are good like thematic elements that you want to look for in your current OChem class if you're taking it right now. So I think that's part of the problem with OChem is you kind of don't know what it's for. You don't know where you're going with it. And if you know, looking at this gives you a little bit of an idea. These are the kinds of questions you're going to have to answer in the long run. So learning things just by memorization isn't so great in organic because, I mean, to be honest, I'm betting that's what a lot of folks did. And that's what happened is you've forgotten so much of that stuff you memorized because you memorized it rote. There was no encapsulating concept around a lot of it. So it tends to get lost. It tends to fade away over time. what you want to try to do if you're currently in OChem or you haven't taken it yet is try to really like pinpoint conceptual things that you can tie your mechanisms to and understand, like, oh, that's why this goes here, or that's why the number of or oxygens change, or that's why this happens, or that's why the negative thing attacks there. So thinking about organic in that sense will be helpful. And I know it's difficult with the way organic is taught here because it's going 100 miles an hour. And to be honest, not a lot of the teachers teach in that way. They teach just really, here's reaction, here's reaction, here's reaction, here's reaction, here's reaction, here's reaction, here's a reaction. And so you sort of get all these things, and none of them seem alike. But if you really dig down and look, like, use the textbook. I know the textbook is a foreign thing these days, but use the textbook to figure out like what makes the reactions similar to each other. They're presenting all these different reactions, but they're really just variations on the same theme. And if you can find that theme, like work together with your peers to find the theme in the different reactions that you're looking at, you're going to be a whole lot happier. Like, really, at the end of the day, if I had to come up with a list of reactions mechanisms that are important, you're going to have your SN1s and 2s. I'm just going to call it SNX. You're going to have your E1s and 2s, EX. Don't worry about E1CB or any of that stuff for this test. You might be taught that in your class. You're going to have to know your radical halogenation. You're going to have to know your electrophilic addition reactions, and there's like oops, I did that backwards. Electrophilic addition reactions, which are AE reactions. And you're going to have to know the sort of the three variations of that: the cyclic intermediate, the carbocation intermediate, and the anti-Markovnikov intermediate, which is the ones that use radicals. And then you've got to know your nucleophilic acyl substitution. And then you got to know your nucleophilic additions. Which are carbonyl reactions. These are all your carbonyl reactions. My writing with this pen tool is just god-awful atrocious. And then you've got to know your aromatic, electrophilic aromatic substitution, what we usually abbreviate SEAR. Electrophilic aromatic substitution, which are all your benzene reactions with the directing groups and stuff like that. You are expected to remember your directing groups, by the way. So this is it though. Like, if you look at categorization, it's actually not a lot because there's just these different categories. If you look at the number of reactions within each category, that's where it becomes overwhelming. So try to boil it down to like these families of reactions rather than every reaction is on its own. Does that make sense to everybody? It's a way to try to decomplexify organic chemistry for yourself.